Chapter 9, Inferences from Two Samples. So to introduce this idea, we have the following scenario. A man buys a new car and is surprised when he's told that he would be given two license plates, but only the rear plate would be installed. The salesman said that while front license plates were required by law in the state, the police don't bother ticketing those with only a rear license plate. He began to wonder if adherence to license plate laws is different in different states. To answer this question, he collected the following data from Connecticut and New York, both which require front and rear license plates by law. And just a fun fact, this was actual data collected by the author of this book. And so we have this table here. We have cars with rear license plates only, cars with front and rear license plates that this author observed in Connecticut and New York, and we have our totals below. So we can see that the proportion of cars with rear license plates only, so this proportion of illegal cars is different in each state. And so we can find that proportion of each, and because this is a sample, I'm going to put a hat on that P to denote that this is a sample proportion. And I could just denote Connecticut as sample 1, and so P hat 1 is given by the number of illegal cars, so 239, divided by the total number of cars, which is 2,049. Okay, and I can find the proportion from sample 2 of illegal cars in New York by taking the number of illegal cars and dividing it by, again, the total. And I can find each of these just by looking. I can see that proportion 2 is significantly smaller. Quick calculation. And we can estimate this to 3 decimal places, 0.117. So proportion 1 is 0.117, and proportion 2 is 0.016. And particularly in decimal form, we can see that proportion 2 is much smaller. But that doesn't really answer our question of significance. So are these two proportions significantly different? And that's what we're going to do in this section, and we're going to extend this idea to means in the next couple of sections. So section 9.1, we deal with two proportions. When we're conducting a hypothesis test for a claim about two population proportions, the same methods from the previous chapter can be used. And so that's this method of hypothesis testing, this general method, and we actually have a flow chart in that last section. And so whether we are using the critical value method or the p-value method, we need some variables, and we need these variables ultimately to find the test statistic. And we know that when we have a P without a hat on top, this refers to a population. So no hat, population. When we've got a hat on this P, we're referring to a sample. And because we actually have two populations, in this case we have the illegal license plates from Connecticut and New York, we will denote these with subscripts, just to show which is which. We've got a sample size from one population, and we've got X, the number of successes in a sample. And we know that the sample proportion is just the number of successes divided by the total number. And our Q hat for population 1 is going to remain the same. It's just 1 minus P hat for population 1. So nothing really different here, but we're just denoting these all as coming from sample 1. And the corresponding notations, same notations, our subscript is now a 2, just apply to population 2. And so because these can get really, really complicated, if you'll notice, this will give us 10 variables. We really don't want to find an equation involving 10 variables. And so what we're going to do is we're going to pool this sample proportion. So pooling this sample proportion is kind of like creating one average sample proportion. And so if we pool this sample proportion, then we can use this P, and this is denoted P bar. And what we're doing is we are adding together the successes and dividing by the total sample size. So this is kind of like a weighted sample proportion. And our Q bar just comes from 1 minus P bar. And so the requirements for this type of test are that the sample proportions are from 2 simple random samples. So same thing as we saw in chapter 7, we needed to come from simple random samples. The 2 samples must be independent, so they must not be connected to each other in any way. And for each of the 2 samples, there are at least 5 successes and 5 failures. And we know we're considering a success. In this case, our successes are denoted x1 and x2. So x1 and x2 must be greater than or equal to 5. Now we have this test statistic. Now this test statistic formula looks a whole lot like our original test statistic formula for one proportion. And let's take a look at that really quickly. So here we've got the test statistic for one population proportion. Can we see the similarities? How in this case our only difference is that we are including both samples. And if we did not have this pooled P and pooled Q, so this P bar and Q bar, we can see how this denominator might get a lot more complicated. And so this is the equation for our test statistic, and we will be given this in the same formula sheet. So when testing a claim about 2 population proportions, the p-value method and the critical value method are equivalent. So this z-score will give us the z-value that we can compare to the critical value. Or we could convert this z-score to a p-value, which we could compare to our alpha. So it's the same thing as we saw in the hypothesis testing. What is not equivalent is the confidence interval method. Now the confidence interval method is really great if we want to estimate a difference between 2 population proportions. If we want to test a claim, we're going to use the p-value or critical value methods.